Electric potential, also known as voltage. Our study of electricity began with Coulomb's law, which calculated the electric force between two charges, big Q and little q. By assuming little q was a small positive charge and dividing F, the force, by little q, the electric field due to the charge big Q was defined, kq/r. The electric field is a property of the space surrounding charge Q. It is a vector field that can be visualized in this PhET interactive simulation for one positive charge. All of the electric field lines point away from the positive charge. The same process will be used to define the electric potential, or voltage, from the electric potential energy, where voltage is a property of the space surrounding the charge Q. Voltage is measured in volts. That's the unit, V. It is a scalar field, as it just has magnitude and not direction, unlike a vector field which has both. A scalar field surrounding one positive charge can be visualized in this PhET interactive simulation. It will soon be represented as a topographic map. We're going to picture this as a hill. Voltage tells us how a single charge distorts the electric space around it. Electric space is not physical space, but describes how charges move in space. Voltage also tells you how much potential energy is in each charge, and if the charges are moving, how much work per charge they can do on another system. So voltage is potential energy per charge. So if we take our equation before, kq/r, so this was potential energy between two charges. If we divide this by the small charge, we get kq/r. This is going to tell us how space is distorted around a charge. Frequently, we're calculating the voltage difference, delta V, between 2 points. By assigning a value of 0 volts to an infinite distance from a charge, the electric potential, or voltage, near the charge is just written as V. Imagine an area of space where there's a positive charge, plus Q, and a negative charge, minus Q. This picture represents how charges distort the electric space around them. The positive charge lifts the electric space up. It's like a mountain or a hill. The negative charge lowers the space. It becomes like a valley. If you were to place a small positive test charge, plus Q, this little charge here, near big Q up here, it would roll down the hill into the valley. And this does go along with what we know already. This aligns with what we know. These two charges would be repelled. So this charge would be repelled from that one and be attracted to the negative charge. So plus Q will roll down the hill from plus Q up here all the way down here to this valley. Midway between plus Q and minus Q, there will be a point where the voltage is 0. So that's like sea level. If a charge was put there, it would not move at all. It would be on flat electric space. Now, place a small negative charge, minus Q, at the bottom of the valley near this large negative charge. It's a small negative charge, so its impact on the electric space is negligible. We don't have to worry about how this little charge affects the space around it. This charge will roll up the hill towards plus Q. This is where the analogy with gravitational force and field fails, as the gravitational force is always attractive, whereas there are two types of electric forces, attractive and repulsive. So yes, you do have to imagine the negative charge rolling uphill, away from this negative charge and towards that positive charge. Voltage is the electric potential energy per charge, which is expressed as joules per coulomb. To make this more understandable, a volt is visualized as a battery, adding 1 joule of energy to every coulomb of charge that goes through the battery. Batteries are a source of electric potential by using chemical reactions to separate the charges and put electrons in motion. Chemical energy is converted into electrical energy. Despite the different physical size of these two batteries, they both have the same voltage, 1.5 volts. That means that every electron that leaves each of these batteries has the same electric potential, 1.5 volts. They each have the same ability to do work. The AA battery just has more chemicals for the reactions, so it will last longer than the AAA battery. We will learn more about how batteries are used in circuits in the next unit. Another helpful equation can be found from this equation here. The voltage difference equals the change in potential energy per charge, by realizing that positive work done on a positive charge by an external force will increase the potential energy of the charge. Rearrange this equation so that we get change in potential energy equals QV, and we see that that change in potential energy is equal to the work done. In summary, the work done on a charge by an external force will change the potential energy of the system. A way to visualize this is we have our big Q up here on top of our voltage hill. If we push another charge uphill from one voltage, let's say 10 volts, to 20 volts, from one voltage location to another, if we multiply that charge times that voltage difference, that will give us the work done and the change in potential energy of the system. To get the total electric potential for multiple charges at a particular point in space, first find the potential due to each charge. Then you can add these potentials together. Since potential is a scalar, there's no direction involved, but there is a positive or negative sign associated with each potential. For example, if there are 3 charges, the total potential at any one location will be the sum of the potential due to each charge. Example 1. For this configuration, calculate the electric potential energy of the system of 2 charges, the electric potential at point P, the work done on a 4 microcoulomb charge to bring it from infinity, over here, all the way to point P, and here are our givens. To calculate the electric potential energy of the system, we just use the electric potential energy formula and input the givens. So first we need to convert the charges into coulombs. So microcoulombs is times 10 to the negative 6 coulombs, and centimeters becomes 10 to the negative 2 meters. So we just plug in our numbers, and we get a potential energy of negative 6.5 joules. Next, we're going to calculate the electric potential at point P. It's also known as voltage. It's also you could think of it as the altitude. So here we have a positive charge, so this is like a big hill, and this is a negative charge, so this is like a deep valley. And so we want to figure out what's the altitude at point P due to this hill and that valley. So we're going to use the fact that we can just use kq over r for each charge. So we have kq over r for the first charge plus kq over r for the second charge. We can factor out the k, and then we just plug in our numbers. And remember, this charge is negative, so this is going to subtract from the overall voltage. And we end up actually with negative voltage at that point. It's a little bit of a valley here. Negative 3.3 times 10 to the 5th volts. Next, we're going to calculate the work required to bring a positive 4 microcoulomb charge from infinity to point P. So we're going to use this equation. The work needed is going to be Q times delta V, where Q is the charge that we're moving inside of the field created by these 2 charges here. So the change in voltage, well, at infinity, voltage is 0, so that's going to be 0 volts. But at point P, it is this, negative 3.3 times 10 to the 5th, which we calculated on the previous slide. So we see that the work required is negative 1.3 joules. The work done by the external force is negative because this positive charge actually wants to go there, right? A positive charge is going to roll downhill into this valley. Remember, this is negative voltage here. So the potential energy of the system decreases by 1.3 joules. Here are two different ways to visualize the electric potential of a system of three charges. Let's start with three charges on a coordinate system. Two of them are positive, one is negative. If we were given the distances between the charges, we could calculate the electric force they exert on each other, the electric field at any location, the electric potential energy that exists in the system, and the voltage at any location. Here's the first way we can visualize this. We can visualize the same three charges using a 3D graph. The positive charges create areas of positive altitude above zero. These are these hills here. The negative charge creates a deep valley below zero. We can calculate the voltage at any location by looking at the altitude on this graph. Also, the steepness of the hills represents the strength of the electric field. So here, where the hill is very steep, that's a very strong electric field due to the charge up here creating it. Whereas over here, it's not very steep, right? Over here, so you can see that the electric field would not be as strong here. Here's the second way. We can visualize the same three charges using a topographic map. You may have seen maps like this before, which are used to represent altitudes at different locations. The dashed lines are ISO lines, also known as equipotential lines. They're lines that show areas that have the same voltage, or altitude. College Board, the AP exam, uses the term ISO lines, whereas most physics texts use equipotential lines. So here you can see that if this line here represents 40 volts, everywhere on this line has an altitude of 40 volts. Everywhere on this line is 60 volts, and so on. Each red line on this map represents the same height value, altitude. The area between lines represents the change in height. So a big space, like here, represents a slow change of height. Whereas when they're really bunched together, like here, you can see there's a very quick change in height. Where in this picture is the steepest incline? Over here we have a region of lines that are very bunched together. This shows that there's probably a mountain at this location. The closer the lines are together, the steeper the incline. So for example, if this is what the topographic map looks like, this is represented by a hill that looks like this. So you can see the steeper, the denser the lines, the steeper, because each line represents the same height change. The closer the topography lines are, the steeper the incline. The topography lines are analogous to equipotential lines. The closer the equipotential lines, the faster the change in voltage. The larger the change in voltage, and hence the stronger the electric field. Remember, the slope of these hills represents the strength of the electric field. Since change in voltage equals 0 along each equipotential line, so if you go around the yellow circle, you're at the same voltage the whole time. If you go around this little red circle, you're at 300 volts the entire time. There's no component of the electric field along these lines, so the field lines are perpendicular. So if you were to draw electric field lines, they would look like this. They would point down the hills, and they would be perpendicular to these lines at all points. The direction of the electric field lines are always perpendicular to the equipotential lines. The electric field lines, shown in blue, are farther apart when the equipotential lines are farther apart. For the positive charge, shown here, the electric field lines point from high to low voltage. They therefore also point away from the positive charge. So this would be like going downhill. These lines point downhill. For the negative charge, shown here, the electric field lines still point from high to low voltage. They therefore point towards a negative charge. So these still point downhill. Remember, a negative charge is going to create a valley in voltage. So these lines are still pointing downhill. Here is another view. The equipotential lines form circles spreading out from the charge. The electric field lines are shown in pink, pointing away from the positive charge and towards the negative charge. They're always pointing downhill. The electric field lines are perpendicular to the equipotential lines. See, these are all 90-degree angles here. And they point in the direction of decreasing potential, which means they're pointing downhill. Also shown in pink are small positive test charges. If placed in those locations, they would move in the direction of the electric field lines, and therefore they would move perpendicular to the equipotential lines. Equipotential lines represent points in space where the electric potential is the same. You could think of that as being the altitude. Electric field lines always point directly from higher voltage to lower voltage. If the voltage is the same along the green lines, then there's no blue electric field line pointing in that direction. The electric field line does not point along the equipotential line. It is perpendicular to it. So these lines are always perpendicular. Not like this. Here they're all over the place, randomly drawn. Here you can see that the electric field lines are always perpendicular to the equipotential lines. For a positive charge like this one, the equipotential lines are positive and decrease to 0 at infinity. A negative charge would be surrounded by negative equipotential lines, which would also go to 0 at infinity. More interesting equipotential lines, like the topographic lines on a map, are generated by more complex charge configurations. When I say these lines are positive, that means they might have values like 10, 5, 2, etc. Numbers, voltages that are above 0. Here are two representations of what the voltage terrain would look like for various charge configurations. So here, these isolines indicate that there must be a positive charge here, since these are positive values for voltage. A negative charge must be somewhere over here, because these are negative voltages. A FET simulation represents 3 positive charges and 2 negative charges. So the darker the red cloud, the higher the hill. The darker the blue cloud, the lower the valley, where black represents locations with 0 voltage. It's easy to imagine a small positive plus Q test charge rolling downhill away from a stationary positive charge. It's harder to imagine a small negative test charge rolling uphill away from a stationary negative charge, but that's how it works in this visualization. Here is the view of equipotential lines that you might see on the AP test. This configuration is created by a positive charge to the left of the 20-volt line and a negative charge to the right of the negative 20-volt line. Note the signs of the equipotential lines in blue and the direction of the electric field vectors in red, which are always perpendicular to the equipotential lines. So here, if we have this line here, this one's perpendicular there, perpendicular, perpendicular, and look, you get these electric field lines that look like this, which is what we know that they do look like, right, when we have a positive and a negative charge. Here is what the side view would look like for this, because this positive Q would be up on a hill, and this negative Q would be down in a valley, and then right in between, there'd be 0 altitude or 0 voltage. So if you placed a small positive charge here, it would roll downhill all the way to the negative Q. A common question you might see is calculating the work done in order to move a charge from infinity over to point B, or from point A to point B. The work done by an external force to move a charge from infinity to a region of space with an electric potential is this equation here, QV, where Q is the magnitude of the charge that you're moving, and delta V is the change in potential between the two locations. So, to move a positive 3 Coulomb charge from infinity to point B, it would take just 30 joules of work to move that charge from infinity to this location here at B. So if we want to move it to B, B has a value of 10 volts. So we can use our equation. The initial voltage is 0 because the initial voltage at infinity is always going to be 0. Our final voltage is this location here with a voltage of 10. So we plug it in here. It's a 3 Coulomb charge, so we need 30 joules of work to do that. The voltage, remember, is 0 at an infinite distance from any charge, as well as the electric potential energy. So if you had another charge at infinity, the electric potential energy between those charges would be 0 as well. Here's an example. Equipotential lines are shown for a region of space. What is the external work done on a positive charge plus Q as it moves from point D to B on a straight line path, so this red path? What about on a curved path, the green arrow? We also want to calculate the external work done on a negative charge as it moves from D to B, on the straight path and on the curved path. First, we're going to be bringing a positive charge from D to B along the straight path. So this is equivalent to rolling a ball up a hill. So we have a positive charge, we're going to be pushing it up the hill to higher voltage. Now remember, there must be a positive charge over here and a negative charge over here in order to even have these equipotential lines. So you could think of this as rolling the ball up the hill towards the positive charge in the direction it does not want to go. So how much work is required? Well, we have Q delta V. Q is the charge that we are pushing, and delta V is the potential difference between points D and B. So, let's erase that line. Okay. The initial voltage location, it's negative 10 volts. So for initial voltage, we have negative 10. The location at B is positive 10. So when we subtract those numbers, the negative signs cancel, and we actually get 20 volts times whatever the charge is. What about if we took the curved path from D to B? Well, electric fields are conservative fields. Therefore, the path doesn't matter. It's path independent. We could go all the way around like this and still end up at B, and it would still be the same answer. So same math. All that matters is where we start and where we end up. So 10 minus negative 10 gives us 20 times the magnitude of the charge. That would give us the amount of work required. For a negative charge, the negative charge wants to go this way. Remember, negative charges want to roll uphill. So if we plug in a negative Q in this equation, the voltage difference stays the same, but now we have a negative charge. So this will be negative work. So remember, if we're pushing this charge in a direction that it wants to go, we are lowering the potential energy of the system, and this will be negative work. Just like before, it's path independent. So if we take the straight path or a curved path, or we loop all the way around, it doesn't matter. It's the same amount of work. The path independence of a conservative field means that when calculating the work done, all that's required are the starting and ending points. This is similar to how the gravitational field is a conservative field, and lifting an object away from Earth is also path independent. All that matters is how far a particle moves vertically from Earth's surface. If an object is carried sideways at a constant velocity at a constant height, no work is done since the energy of the object has not changed. So for example, if you lift a basketball by raising it like this, it doesn't matter. The sideways motion didn't have anything to do with the amount of gravitational potential energy added. All that matters is the starting height and the ending height.